Hello everyone again. I hope you succeeded to connect to this second session. Uh, so I'm back. So it's still Vincent from Parasis. So now I would like to introduce you the next speaker. So the next speaker is Takashi Yamada. So from JSOL Corporation. So Takashi is a manager of JMAG software. I'm working with him since now 14 years, since a long time. So I know him a lot, and it's a great pleasure to work with him. And I have to admit that for you, our customer, I think it's also a chance. Takashi is very motivated to deliver you the best simulation software for electromagnetic analysis. But his goal is not to provide only a software. He really wants to be a partner with you and to work in close collaboration with you. So please ask him a lot. You need to ask more change on JMAG, but it's a pleasure for him to adapt JMAG to your need. So please, Takashi, welcome. Thank you for your presentation. And I hope you will enjoy the session for everyone. So Takashi, it's for you now.
Okay, thank you very much. Try. Yeah. I hope it's now working.
Yes, we can see your screen. You can start.
Okay.
Thank you.
Okay, thank you. Thank you, Vincent. Thank you very much for very nice, very kind introduction. Yeah, yes. This time, I try to share my idea of GMO development with you, and then hopefully I can get some feedback, a lot of feedback, and I'd like to improve our solution for you. That's the main purpose. And before that, I'd like to thank you so much for Parasis people for this great event, and then I appreciate your great effort for effort for this the event. Okay, let me start. So this is my presentation. Okay, doesn't work. Sorry. Oops. Okay, this is agenda of my talk today. I cannot cover everything of JMAG, so I picked up important technical topics for coming next years. So these 6 items are quite important for you and to provide good solution for you. So speed, loss calculation, multiphysics, optimization, Mill and Hill, and GUI. That's the topics. Okay, so first is the speed, left-hand side top here. So I will skip why we are doing this. Probably you know what's the goal of JMAG. We are pursuing super high accuracy in electromagnetic simulation. So to achieve that goal, we need very, very high speed calculation. So that's why we are putting our effort to this. So okay, this is a roadmap of our parallel solver. So goal is to achieve 400 times speed up using 2000 cores by end of next year. So this is a top right here. It's a goal. So we are now the middle here. So we are releasing next version, which is version 20 end of this year. And the goal is to exceed 200 times using 1000 cores. This is a goal this year. Okay. And the status at the moment, we have some time to release next version, but so far it's good. So this is a 200 line, and this gray one is the current version, and this one is a new version. So we're testing, so score is quite good. So probably we can exceed that line in general. And probably understand some people say that I don't have so much cores. Don't worry, we have a good solution for you. So we improved a lot GPU solver. Then we can use GPU solver as accelerator. So this is a new solution. So this blue line is usual SMP solver scalability. This is good, but on top of this line, now we have another line. So this is speed up, and this is number parallel. So using the GPU, you can double your speed. So this is a new solution. This is coming probably next version. So this is some result of GPU. Okay, this is a parallel solver roadmap. Okay, so then of course, as I said, parallel solver, we hope we will be able to achieve 400 times speed up next year. Then what next? So we're now shifting our effort from the parallel to other items, which are convergence enhancement and the process efficiency improvement. As a convergence enhancement, probably you know that JMAG is employing the iterative solver. Then the convergence performance sometimes affected by some other reasons, many reasons. One is the poor elemental shape or some very tough nonlinearity, or you need to solve transient steady state, get steady state for like a PWM type, many type steps, those things. But we need to somehow deal with this tough situation. So we are now looking at some technology to improve this one. This is the one technology we're looking at. Then probably we will introduce this technique next version or after. So this is quite effective for high aspect ratio elements. So aspect ratio is just ratio between this edge and this edge. So poorest element has very high aspect ratio. So this happened like this kind of a shield problem. So you have a very thin plate here, and you need to have a very thin element to deal with eddy current. Then usually the ratio is going up, then iteration goes up. This is a big problem. But with new technique, this one, you can mitigate this effect quite a lot. So we will introduce this kind of technique. This is one. Then another issue is process efficiency. So this means even your problem is very small problem, like 2D and probably 10,000 type size problem. But if you need to solve those problems 10,000 to 100,000, it takes time. So file I/O or some meshing or data transfer, process synchronization will be a problem. So we are now fighting with those issues. Then we will improve our solver and process. Then to achieve 10 times by end of next year. This is our roadmap for small and mid-sized problems with many steps and cases. So we have this kind of roadmap, and we are now here. I hope we can achieve 5 times faster than 2 years ago. So this is our goal of this year. We are working on this one. Okay, that is a speed. So next is that iron loss. This is a quite tough issue. So far, what we have done is this one, transition from Steinmetz-based, very classical loss calculation method to we call P1D. This is a pre-model plus 1D method. The problem was this classical approach. It is good, but the problem is that it cannot deal with minor loops. Then this also cannot deal with non-sinusoidal waveform. And then limitation, it has a limitation in frequency. But these three items are critical for advanced machine, today's advanced machine. So you have a PWM and you have lots of higher harmonics in a machine. So you cannot neglect this one. So to deal with this one, we introduce this one. And this is working. And then not all, but many people started using this technique to improve the accuracy of your estimation of loss. So this is some cases. You can find many examples in our user conference proceedings. But of course, that P1D is not perfect. So hysteresis loss is okay now with pre-model, and eddy current is okay with 1D model. But we still have a problem here. This excess loss. This is a quite nasty problem. So how we can solve this one? So we are fighting with this problem today. Okay, this is a summary actually. So now here we have 3 lines. So this is the measurement result. This blue line is measurement result of loss variation from when you apply DC bias. So if you are adding some DC bias, so of course loss increase. So of course, Steinmetz-based approach is okay for without any bias, but you add lots of bias, then of course you have no hope to meet each other. This blue line is the measurement. Then P1D method, new method, is okay with the bias here. So this region, you don't have so much excess loss, so it's okay. But here, you have a lot of problem here. So this is the start of this problem. Then, of course, there is a technique to correct this gap. And this works for relatively low frequency. So 1 kHz is okay. So therefore, practically today, it's okay. But now frequency is going up. So now you have a problem, and we have a problem. So we are working on this past 2 years. So then it seems we are getting some solution. So this is quite new latest result from our side. So now we have this red line. So it's quite good. But we are still validating this method, changing some materials and conditions. So this is the current status. And of course, I like to put this capability in JMAG as soon as possible. But anyway, this is the current status. Right. So next one is multiphysics. Okay, many people say that now we have a magnetic solver and we have a structural solver and we have a thermal solver, CFD. Now we can do a multiphysics. Sometimes it is correct, but not always. So just bundling multiphysics code is not multiphysics. Sometimes, or many times, really you need tighter coupling and very good integration. That's very, very important. This is what we are doing today in JMAGs. So actually, JMAG has a very good solution for induction heating. So this is a very tight coupling. So then you can solve induction heating problem very nicely. And many people, our customers, are using this solution for the machine design. Then now we are trying to connect magnetic and the structure. It seems probably it sounds very simple. Probably you wonder what's the problem. Okay, this one. So we have we took this very simple the problem. So this electromagnet is the core and the magnet, and it's surrounded by the frame, steel frame, very simple one. Then try to solve the vibration here around here. So the usual way is we can calculate the force with magnetic field calculation very nicely. And you can apply this force history or spectrum to a mechanical model like this one. Then you can get displacement or velocity of the sound pressure. And the other way is a bit complicated, but you can do this one. You can just calculate exchanging the solve magnetic field and structure, exchanging the force and displacement. Probably you notice that when you apply the force here, this plate will deform, then magnetic resistance will reduce. Then of course, the field change, the force change. So actually you need good interaction here. Okay, let's see the result. So this red line shows one way calculation result. By the way, horizontal axis is the frequency, and then vertical is the displacement. And the two ways, this one. So the peak point is different now. And the right-hand side is showing the displacement history at this frequency point. So this is a very simple problem to solve, I think. The many people is doing this one, but it's not really the perfect. So of course, not always, but this is an important technique to have. So since JMAG has a magnetics, structure, and thermal, so we can combine quite closely, and we can realize very tight coupling. Then we can solve this kind of problem, and you can have more accuracy with JMAG. So this is something we're doing in JMAG. Okay. Of course, we are not denying the solution working with others. JMAG is open and quite neutral to any systems. And we are expanding our interface with other third-party package tools. So now we have those partners, and we have very nice interface between them. And of course, we are quite open. Then we will expand this interface. So this is a current situation about the multiphysics. Okay, next is optimization. Okay, optimization is very important. Probably I don't need to iterate this one, but sometimes still people do not do optimization so much. But I mean, this is necessary, really. So because you have lots of objectives and constraints. So even your model is a 2D or a simple one, your objective, you have many objectives. Therefore, solution space, feasible space will be a very, very small. So therefore, almost impossible to find out this small region by hand or with experience. Even you are a very good engineer, it's very difficult to find out this small space. You need automatic optimization. Okay, but problem is that you have to do lots of calculation in this type of optimization process. So for example, this case, you need more than 20,000 cases to achieve optimized design. So even each loop and making the model, the mesh it, output the data and then submit, then solve, and the post-processing. So this is simple, but iterating this one 20,000 times with no problem, it is not so easy job. Also, speeding up is quite difficult. So, I mean, each process, each point is okay, but sending some data or fetching data or doing processing and visualizing this, those each step takes some time. So this is a big problem today. So then we are now improving this efficiency. So with 3 times faster than last year. This is our current work and objective. So this is what we are doing, and we will improve more next year. Other problem is that so we have to do 20,000 times FEA problem solving. Actually, FEA itself takes time. Therefore, if we could reduce number of FEA, it will help. So we are looking at that point. So one of the, this is quite the usual approach to reduce design space. So using DOE or just simply using FEA, you could reduce design space. Then you can limit design space, then of course you can reduce, you can accelerate your calculation. Now, what we are looking at the reduced order model to skip this part, to go through very fast this region. So we started this development, and as a first step, we will use equivalent circuit model for reduced order model. So this is the right-hand side. This is a result. This is without reduced order model, and the right-hand side is with reduced order model. So you can reduce the time, process time greatly. Then of course you can get the almost same feasible region space. So this is the first step. Then after that, we will introduce surrogate model, probably based on artificial intelligence type. So this is our plan for this optimization technique. The other interesting topic is topology optimization. This is still optimization, this different type of optimization. So this optimizer will find optimal topology for you. So this is an interesting example. Okay, this is the usual multi-objective optimization, which I just showed before. So you can get this one with design parameter optimization. But you can restart optimization with topology optimization from this one. Then this topology optimization will find some other topology. So this is a result of topology optimization. Then now you can somehow parameterize some parameter from this shape. Then do further parameter optimization. So then result is interesting. So this is a palette front, and then this is the same one, just a map here. Then this is the result after the topology optimization. So you can advance this front from this point to this one. So actually, this is not really optimized solution. This is the optimized solution. You cannot achieve this point without topology optimization. So topology optimization is quite powerful. So of course, topology optimization is a good technique, but that we are not perfect. Actually, we have two issues. One is monetization. Of course, you like to find good topology for magnet. So the region-wise, it's just okay. You can find. But problem is that what's the magnetization direction? You have an infinite number of possibility. How to find this one? It's quite difficult. But we have some solution for density method. By the way, we have two types of topology optimization approach. One is density method. It's a quick one. And then we have another one, energy net approach. This is a more powerful. So this year we will implement a solution for this issue this year on a density method. Then next year we will put it in energy net method. So this is a plan. And the other one is simply speed. Of course, you need lots of calculation. It's a modern parameter optimization. So you need more power, and we need to improve efficiency and new technique to accelerate. Probably we need to introduce ROM, reduced order model idea, for this one as well. But anyway, we will do this one. So then somehow we will speed up 10 times next 2 years. This is our plan. Okay, next is that Hill. So actually this is about JMAG-RT. So probably you know that JMAG-RT is a model for Miller and Hill from JMAG-FEA. This accurate and high speed. Okay, so request from the market is this. Now JMAG-RT is quite good to simulate normal mode for test or system design or control design. But now people want to use JMAG-RT for other stages purposes. One is calibration of the control parameter. But to realize this one more, we need more accuracy. Especially, we need to have good estimation for loss. This means this torque, the loss affect torque. So this is very, very important. This is one. The other one is a failure mode. But okay, let's have this one. This is one of the results recently we have done. So we introduced new loss model in JMAG-RT. So using this one, you can reduce the estimation error from without iron loss to a new iron loss model. So left-hand side is without, and then red one is with. So you can see lots of improvement, especially for this one, because this technique is very good for PWM input. So it works for this range, low torque range. But this is an important technique. So we introduce it. Now, of course, we will expand this one to some other regions. Probably we need to improve this region as well. So that is next our task. And then to deal with failure mode, we need flexibility, and of course, JMAG can do that. This is just example of failure mode analysis of 6-phase PMSM. The one of the power device broke down, and of course, wave deteriorated. So JMAG is now can deal with this kind of problem. But problem is that takes time to generate the data, lookup data to cover very strange combination of the current. So now we are enhancing the speed of model generation time and then execution time. This is one of the results. Okay. And otherwise, we will expand JMAG-RT capability not only toward high fidelity, but also more opposite side, abstract side. So then this means now JMAG has an efficiency map capability. Then we will unify that capability into JMAG RT function. So then JMAG RT will be able to cover very abstract level to a very high fidelity detail level. So this is a static simulation, this is a dynamic simulation. And of course, we will expand machine coverage. We started three-phase PMSM induction machines. Now we have a dedicated model for six-phase PMSM, and then dedicated model for synchronous machine, and the probably resolver. Now, of course, today we have a generic model. It can cover resolver today. So, but we will have this one. Okay. Yes, I'm almost finishing. So final point is GUI. Probably you can see a very nice demonstration by PowerSys probably tomorrow. About this one. Last year, we introduced new GUI, which we call analysis parameter view and dashboard. The concept is very simple. You can see all parameter in a single panel. It includes geometry parameters, condition parameters, material equation, everything. All parameter is displayed on a single panel. So you don't need to drill down very deep and come back. You don't need that. You can see everything on this screen, this one. And the same, similarly, you can see selected result in a single panel, I mean, post-processing. So very easy to compare and very easy to investigate what's happening in simulation result, compare the graph or a different type of the contour. So we had this one and we are improving this one, many point. And what we are going to do is this. So you can access any parameter and you can check any result. So probably it's maybe nice to access this APB and dashboard from outside JMAG Designer without activating JMAG Designer. Very easy to check the parameter, change the parameter, then check the result. So it's very quick. You don't need to activate and then loading the data. You can do that, all those jobs without JMAG Designer. This is our plan. This will come next year. Actually, what we have done is this. So JMAG, I'm showing the hierarchy, the architecture in JMAG Designer. So JMAG Designer consists of 3 layers. One is a base function, like a geometry editor or a condition setting processor, and the mesh and the solvers and the post-processor, then parametric system and the sub-tools. This is a basic function in Designer. Then we have we added service functions to make it easy for you, like a geometry template, analysis template, coil template, and automatic optimizer. This is a service function we call. Then furthermore, we added application functions. Those functions are more application dedicated function. Today, mainly for rotating machines. So we have winding editor, magnet editor, efficiency map, and ramp parameter. This is coming next version. So we have this very high level application functions. So then APV and dashboard can access any function from this top level. So very quick direct access. Then we have another idea. So since we have this kind of very high level function, probably we could make application dedicated GUI to realize simple to use. This is another idea. So that is actually JMAG Express, but it's different from today's JMAG Express. It's more powerful. So actually, this JMAG Express is actually it's a JMAG designer, as I explained. This new GUI is just the face of JMAG designer. But of course, it covers existing function of JMAG Express. You can get characteristics and you can do a sizing. Of course, you have a lot of geometry template and the summary calculation, efficiency maps. Adding on this, now you will be able to get like waveform, like a coin torque, very detailed calculation, and then flux field plot, flux line or the contour plot. Of course, you can generate MRT. So this is coming, and then good point is that again, since this is actually JMAG designer, therefore very easy to switch to JMAG designer. So you can jump in very detailed calculation, or you can pass your model to your colleague who is using JMAG designer. Seamless, of course. And here, again, this is the JMAG designer. So you can use full power of JMAG designer. It's quite powerful one. So we are now developing this one. This is not solution we can provide this year, but next year we will ship this one to the market. So that's all my talk. Thank you very much for your attention and your patience. Thank you.
Thank you very much, Takashi, for your presentation. I will, at my turn now, share my screen just to explain you how you could ask question to Takashi. So I hope you can see my screen. So Takashi, can you confirm you can see my screen?
Yeah.
Okay, very good. So I think everyone can see my screen. So this is in fact the Ruba platform we are using today for the conference. You need to go in the session Q&A. Okay, click on it, and if you got the list of all session, so if you want to ask question to Takashi, please click on View Question, and you can ask a question there. Okay, so Takashi, you have first question there, so maybe you can take your time to reply to everyone, but please ask question here, and we will send you some reply. Okay. Now, yes, it's 20 to 12, so I think we can close the session, Takashi's session. So thank you so much. The next presentation will be in 20 minutes. So just as the real session, we can have a coffee break. And please come back at 12 to look at the next station from some customers. So thank you so much, Takashi. Thank you for your attention.
Thank you. See you soon. Bye.
Bye-bye.